Here's the address, so you can pin it down. And if you want to join, please sign in that form here so that the reservation can be made. Okay? Wednesday evening, 7:30. Okay. Good. So, and now the lecture starts. And it's Introduction to Neural Networks. But before I start, I would like to say a few words about myself and where I'm from. And it's on the board here. This is the institute where I'm working at, Nordita. It's a Nordic Institute for Theoretical Physics. That's just the homepage. When you go to www.nordita.org, you will see that. And you see it's an institute for theoretical physics. There's no machine learning in the title. It's theoretical physics. So we do physics. We're doing all sorts of physics, from astrophysics, cosmology, soft matter, to hard condensed matter, topological insulators, and all sorts of things. I'm in statistical physics and soft matter, and this is where my connection to machine learning lies. There are statistical physics tools, statistical physics methods that you apply to understand how these artificial neural networks work. Okay, and this is also the idea behind my lecture here, that I do not want to say to you, okay, look, this is this architecture you can use for this task, and it will do this and this and that. And there's another architecture, and you can do this and this and this and that with that architecture. I would like to try to answer the question on a very basic level: how do these things actually learn? How do they manage to do all these tasks we are asking them to do? And for that, I will go to the very, very, very basics, which are already like 70 years old or something like that, almost. And I will try, my goal is to explain to you on this very basic level how learning in these machines works and how they succeed in what they're doing. And then we will see how far we get. Maybe there's time to make some connection to more modern architectures. The literature I've been using to preparing this lecture is basically these three books. And you see it's also always like Learning within Networks, an introduction for scientists and engineers, or the second one. So the two first I mainly used, a little bit the third one. A biased introduction to networks and old school machine learning. Old school machine learning means like applying statistical physics tools and trying to understand how they work. Okay, so that's my goal. And I have a question for you. Who is actually working with machine learning here in that audience? Okay, that's not so many. Who is here to learn about machine learning? Ah, that looks good. Anybody ever heard about the perceptron? A few, okay. So this is the main thing we're going to talk about and then start from there. Right, so, and because I'm a theoretical physicist, I'm using the blackboard. Okay, so that's how it works. Yeah, I will start. So I think everybody can see, right? Yes, good. I will start with motivating artificial neural networks from what we find in nature, because these things we're using nowadays, they got a lot of inspiration from key aspects of biological systems. So if you just look I mean, this is a very, very rough sketch, and maybe we learn a little bit more in your lecture, I don't know. If you just look at one neuron, it looks roughly, very, very roughly, like that. You have a cell body, which is called soma. And then there is some long thing, which is the axon. And then they has some endings, which end in synapses. Something like that. So here are synapses. And here there's the dendritic tree, which is connected to other networks on that end. Something like that. Dendritic tree. So here are other neurons that come in. Synapses from other neurons are connected here and here, everywhere. And also here are then, these are connected to the next neuron. And an input that comes in here is basically an electrical signal that is translated into a chemical signal across a gap that is connecting the synapse with the dendrites here, and this chemical signal changes the potential, the membrane potential at the cell. And if the membrane potential reaches a certain threshold, this whole thing starts to fire and sends a signal along its axon, which is transferred to the next neuron that is connected here, or neurons. So the important observation is that if the membrane potential due to incoming signals exceeds a certain threshold, then the neuron fires. It creates a signal. And a signal going across the axon connecting to the next neurons. And this whole thing influences the potential and activity of all the postsynaptic neurons that come here. So there is a whole system of interconnected neurons are basically, in that abstract picture, a complex system of threshold units that start to fire when you reach a certain level. And they're influencing the activities and signals in the whole network. Okay, transmitted along the network. And then we also know that these things somehow learn, okay? I mean, the neural systems are able to store information or learn tasks. So there is some process which is called learning. And also here, I mean, this is extremely simplified. What people have been inspired by in this context is the so-called Heppian rule. Hep rule, which says, I read the original quote, when an axon of cell A is near enough to excite cell B and repeatedly or persistently takes parts in firing it, some growth process or metabolic change takes place in one or both cells such that A's efficiency as one of the cells firing B is increased. So did you understand that sentence? more or less. So what it says is that neurons that fire together, they wire together. So they connect, they increase their strength together. This is the short sentence, the key of that Hebb rule. And this is called synaptic plasticity. So the neurons learn by changing the strength of their connection. When they often fire together, they increase their strength, and in that way they learn. As said, that's of course not the whole story, and it's an extremely simplified picture, but this is what inspires many of the learning algorithms that you find in machine learning. Often you maybe have heard already about the Hebbian learning rule in many contexts. Okay, so we are going to simplify and turn these insights into a abstract representation, and from that construct artificial neural networks. So the first key ingredient is what is called the McCulloch-Pitts neuron, after the guys who invented it. And it's based on the idea that, as I mentioned already, that artificial neural networks, that they are highly idealized or abstracted concepts from biology, let's say. So what I said over there. So the simplification consists in that we say the neuron can have just two states. It can either be inactive, and then we assign a -1 to it. Very often you see that the inactive state is 0, and that can be mapped to each other, obviously. But physicists often prefer the -1 because it reminds them of spins. So we use the same techniques there. And active is the +1. Okay? And then we want to mimic this behavior here. And this is done by a so-called activation function. Which I abbreviate by G. And it's something like that. So from -1 to +1, the state is changed if the signal strength B exceeds a certain threshold theta. Okay? Here in that area, the neuron is inactive, it's state -1. This is the threshold. And once the signal, the B is the incoming signal, as you will see, exceeds the threshold, it jumps to active. Very simple. That's the simple representation. And this is called, this is the signum function. So this is signum of B minus theta. And signum is -1 if the argument is negative, and +1 if the argument is positive. Okay. There are many other possible choices for activation functions which people use nowadays. So the basic idea was this, and this goes back to the what did I write down? 1950s, I think. This neuron here, McCullough-Pitts. But then you can use many other activation functions in modern application. And we will also use a little bit of those later. So here, for instance, there's a disadvantage that it's discontinuous. So if you need to do something where you have to differentiate, it will not be so easy. So you can use sigmoidal functions. For instance, this one, which I appreciate by sigma of b, it's 1 divided by 1 plus e to minus b. And it looks very similar to the one above, only that it's smooth. Okay, so it's between +1 and -1. And if I write it like that, I don't include a threshold, so the switch here is at 0. And if I include a threshold, I can shift it around. Okay, a similar function that looks very similar like that one is the tangents hyperbolic. It's also used. And then there are even simpler functions like just the linear unit or the, no, I cannot read that. So the linear activation function. It's really just a linear function. Or what is called the ReLU unit, rectified linear unit. So for positive values, it's like the linear unit, and for negative values, it's 0. It looks like that. These are all activation functions that are used, and many more. But we will encounter those later during the lecture. Okay, this is how you can present individual neurons, artificial neurons. And then you have to connect them if you want to build a network. And the connections between neurons, they are represented by links of specific strength. And this is a real number. This real number tells you how strong the connection between neurons is. So for instance, if I have a neuron here, of that type with a certain activation function, so circles in my sketches will represent the neurons, then you have connections between them. There are maybe more here, somewhere outside. This is neuron I, J, K, and then the connections are typically written by W's. W's IJ, WJK, WIK. And these W's, they are, as said, real numbers, and they are called weights, or also sometimes synaptic strength. Okay, and now you can, of course, imagine that you can, in principle, create any network of neurons you would like to, but there are I mean, in particular in the beginning days, there were basically two types of networks people considered. And the first one is the fully connected recurrent network. So it looked something like that. So every neuron is connected with basically every other neuron. Yeah. Here. This is, for instance, one of the networks that is of that type is the so-called Hopfield network, which is used to store patterns, for instance. The second type is a feed-forward layout. Feed-forward layered networks. So you have typically sketched like that, different layers of neurons. Doesn't need to be the same number of neurons, and then you have connections that go forward from one layer to the next. And there are typically no connections that jump over layers or that go backwards. So there is a direction here, feed-forward network. And in the beginning, when they were invented, they were called perceptrons, multi-layered perceptrons. They were invented by Rosenblatt. In 1958 already. Okay, so these are two basic architectures. Nowadays, of course, these concepts are mixed, and they are, for instance, feed-forward networks where you allow for recurrent connections or for when you skip layers and things like that. Or you build in, if you have reservoir learning, you have feed-forward part, and then you have some strongly connected, and then you continue with feed-forward again. So it's all like adjusted to the needs you have. But these are the very basic types. By the way, feel free to ask questions whenever you have. Can interrupt me. Yes. Feed forward. This is layered networks. Layered. Okay. Yeah. Is that what you mean? Yeah. Well, as far as I know, you can connect the layers fully, so that might be the starting point, right? Where you have start here and connect to all the others, and so on. And this is, I think, the typical starting point for deep learning if you have many layers. But then you have extremely many parameters. So one of the learning strategies can actually be to thin out the network and get rid of connections you don't need during the learning process. And then it's not fully connected anymore. Okay, more questions, yeah.
These GPT functions, they are the particular case you use the one type these functions, or I choose the function.
Ah, okay, yes. So, as said, this here is largely inspired by the idea that you have to go beyond a certain threshold to get an activation. And that's the simplest function. And then it's nice because it only has two values, so you can often do calculations and things. But it has a disadvantage because it's not continuous. So you take smoother versions. And then you find that these also have problems sometimes. I will come to that because of these parts here. And then you may have to use other activation functions. So it depends largely on the task and on the stability of your learning algorithm, what you have to use. It's part of the design, I would say. And there are more I haven't mentioned. There's, for instance, an activation function which is called softmax, which chooses the output neuron which is strongest. And then you can interpret the output as a probability that the network thinks, okay, a certain task has this outcome, something like that. Yeah. Okay, so from with these general things here, we can actually simplify even more. And this is a type of network which I like to call the perceptron. So it's the simplest network, feed-forward network you can imagine. It has just one layer of input neurons, N of input neurons, just one output. So here's the input. Here comes the signal in somehow. It's connected, all of them are connected to one output. And the weights here are collected in a vector, so W with one index I, with this being 1, 2, 3, 4, 5, and so on. And here at the output, you have some activation function, G of B. So the Wi are the weights. The input is also a real number, which comes in here. Then you calculate the strength of the signal coming into the output unit. This is the B here in the activation functions as the sum over all incoming signals. So here is the input coming in, x1, x2, x3, and so on. And you multiply it with the weight vector connecting this input neuron to the output. So this is x1 times w1, x2 times w2, x3 times w3. You add them all up and you subtract your threshold. Okay, and now if this is positive, then you want the neuron to produce an output, to fire. If it's negative, it's inactive. This here is called the local field of that output neuron. And the output itself is S, inspired by spin for the physicists. And in that case, it would be the simple signum function. So that is what the perceptron is doing. Okay? Are you with me? Good. So if the output times the weight vector are beyond a certain threshold, then it produces an output +1. Otherwise, it will be -1. Yes? Yes, yes. Yeah, I changed the notation a little bit. That's all. Yes, yes, it's common. It's common, yeah. Thanks for the question. And this thing here is extremely simple, right? But surprisingly important in the whole business, because it was one of the very first models that you could actually analyze in detail and understand how it learns and what it's doing. And for instance, there are theorems about this network that show that, for instance, that when these networks can find, when there is a solution to the task that is given to the network, it also finds that solution with a certain training algorithm. So that can be proven mathematically, which is very interesting and powerful. And then it's also some kind of prototype for what people built upon that. I mean, you can, for instance, the feed-forward networks, they can be viewed as if being constructed from smaller perceptrons. One of the guys working in the field said, it's Manfred Oppenheimer. He said, this is the hydrogen atom of the neural networks. So it's a very basic thing. Yeah, it's a basic building block for more complicated networks. Okay, what is the task you can give to such a network? And this is called, the task we give to the network is called a classification problem. And it's the following. You have given P input output pairs. They come from somewhere. So you have vector X and output S, and they're labeled by the mu here, Greek mu, and the mu goes from 1 to P. So that means that for every output X I give to the network, and I write this as a vector now, this X with a line underneath means it's a vector collecting all the components. I want, if I give this to the network, I want this output here. And I give it an index T, meaning training or target. So this is the target output I want the network to produce. So yeah, I can write that down so that you see that better. So X mu is a vector, X1, X2 to Xn mu. And the S training is either -1 or +1. And the task is to find a weight vector W, W1, W2, W3, Wn here, such that the output that the network produces fits the target value. So this is the output the network produces for a given input, and I want it to be identical to the target I give here. This is also called the perceptron storage problem. And actually, where's the speaker of the previous lecture? We have seen, you gave an example of such a thing, namely with the three, it was somewhere here, with the three areas under the curve, right? You have a point in that space and you assign to it a target, namely the shape. And then you want a network that trains this and recognizes the shapes. And this is an example for what you have here, just in that very simple architecture. So you have your inputs, your specific values for the areas in that case, and you have the output, which is a shape. So here this is simpler because you have only two values and a simple network, but you can generalize it. This is the idea. So you want a network that can classify things. An example, very, very simple example, is the following. We look into n equals to 2. So just 2 input neurons, 1 output neuron. And we look at the function, which is the Boolean AND. So that means x1, x2, and the output would be like that. So the input can be +1, +1, -1, +1, +1, -1, or -1, -1. And the logical Boolean AND means that both have to be active to get an active result here, like that. This would be -1, this would be -1, and this would be -1. So that's our classification task. We have, in that case, P is equal to 4. We have 4 input patterns with a target output. Okay? And since it's in 2 dimensions, we can make a sketch to visualize it. x1, x2. So this here is called the feature space. This is exactly the same space as we've seen before with the different areas. That was 3-dimensional because you had 3 values. And we have only 4 points in that feature space in our case. Namely here, where the output is +1, and for the other ones, it's always -1. So I take a circle for +1 and an open square for -1. Okay, do you see that? That is representing this table. Okay, so what does it now mean to learn this relation here? What does the network has to do? How do the weights have to look like? To understand that, we take a closer look at what is written in that activation function here. So in that case, the output is signum of x1, w1 plus x2, w2 minus theta. And in 2 dimensions, or in any dimension actually, this is simply a scalar product. Right, a scalar product between 2 vectors. So if I sketch that, and for the case that our threshold is 0 for a moment, What does that mean here? So if I sketch a vector W here, I assume I just have a weight vector, vector W, then the sign of that is, the scalar product is the length of x times the length of W times the angle between the two vectors. So that means as long as the cosine is positive, the output will be positive. So as long as the x values are on that side here, because then any vector has an angle that is smaller than 90 degrees, will produce a positive value here. So on that side, the output is always positive on that side of that line, okay, which is defined by the direction of the weight vector. On the other side, it will be negative. So and if you have a non-vanishing theta, you can write the scalar product as you can write the vector x as an other x tilde minus theta, and the x tilde, the d here is the distance from the origin, and then the plane is like that. And here is the W, and the vector x is maybe here. So this is x, and this is x tilde. So I'm not sure if you can see that. I hope so. And then you split that apart here, and then you see that it's x tilde times W plus d times W minus theta. So that means that this theta here, if this is 0, then it's the distance from the origin. So it shifts basically this dividing line away from the origin. This is what the threshold does. So it moves it to the other side. And then you have the same thing, that on that side S is positive and the other side is negative. Okay? And now you actually see that you can solve this problem here, right? Because all you need is to draw a line somewhere here that separates these two regions, where the output is positive and here where the output is negative. So any weight vector that somehow separates the plane into these two regions solves this classification problem. And it's not necessarily unique, as you can see. So it works for this simple example by inspection, but in general, how do we find the W? And what we do is we use learning. Okay, we train the network in a certain way and let the network learn the right weight vector. So what we do is we start with an initial vector at time 0, and this can be simply 0 or it can be randomly distributed from some appropriate distribution. There are different possibilities. Then we, at each time step where we learn, we present one or several or all training examples to the network. So the training examples are these, the ones we want to learn. These are our training examples. We present them in some way to the network and compare. I will specify in more detail what I mean by that. The output of the current weight vector times the current training example I present with the desired one. Okay, and then, depending on the outcome of this comparison, I update the weights. So the weights at t+1 are the old weights plus some change. And this change should be small in general. So that's the idea behind learning. That we update, we start from some choice for the initial weights, and we somehow update them depending on our training examples to hopefully find a solution which can solve this problem. And such a setup is called supervised learning because the output examples have labels. So these things here in the space I sketched, they have labels, +1 or -1 in that case. So this is one of the key learning paradigms. Then there are examples where your training data, they don't have labels. You just have this. And this is unsupervised learning. And it's typically used for finding clusters in data or structure or data compression, dimensional reduction, and things like that. And then there is yet another learning paradigm, which is called reinforcement learning, where you train your network in response to the environment. So typically there is some kind of reward function which is evaluated during the training, and the network reacts to that. So imagine a robot that has to navigate to some environment. So there's an interaction with an environment, and depending on the state of the environment, the action the network, the robot takes to reach a certain goal is trained. But in that lecture, I will focus mainly or almost exclusively on supervised learning. So, any questions? No. Nobody has a question. Nobody wants to ask, how do I choose delta W of t? So how do I actually find some decent training algorithms that work? So for these simple perceptrons, there are two basic strategies. And this is why it's, I think it's quite important to look at the very basic case, because everything we do right now is based on these ideas. So the question is how to choose delta W of t. And this is then, if you find a way to choose them, this is called a learning or training algorithm. And we consider two strategies here, which I want to work out with you. And the first one is an energy-based learning. It's basically gradient descent. And the second one is an iterative training algorithm. Okay. Yeah, I think we can have a look at the energy-based learning rule before the break. You're still with me, right? Or are you longing for coffee? Okay. So the idea here is to perform a gradient descent in an energy landscape. So you see, this is very physics motivated, all these things here. And for that, because if I want to do gradient descent, I have to take derivatives. So the signum function would not work. And for that reason, and for simplicity, we consider the linear activation function. So we take g of b equals to b. It's linear units. So that means that the output the perceptron produces is simply the sum over all wi xi mu. Okay? And we set the threshold to 0 for simplicity. So the classification problem we have it means that I want that this S mu are equal to the training mu's for all training examples I present to the network. Okay, this is my goal. This is what I want to reach. This is for given input x, mu, the output, and I want it to be the same. So this is a linear problem, so it can actually be solved directly by matrix inversion. It has the formal solution. I don't work out the details. I just want to give you the structure, that the Wi are equal to 1 over n, sum over all mu, S T mu, and here I have a matrix Q, the inverse minus 1 mu nu xi mu, where the matrix Q is given by 1 over n x mu times x nu. So you can easily check by plugging this here into this formula that it actually solves that problem. It's a linear problem. So that means that if I want to solve it, this matrix Q has to be invertible. And that means that all the examples, the input patterns, have to be linearly independent. If these vectors are linearly dependent, then I cannot invert the matrix. It's a result from linear algebra. So that means here that Q must be invertible. So the x mu must be linearly independent. So that means that I have a necessary condition that namely the number of examples I have or training patterns I have must be smaller than the dimension of the space. Because if I have more of those, they are automatically linear dependent. So you see already from some simple considerations, I get some ideas about the situations where these networks can learn or not. But now, I mean, in general, n might be quite large, so p might also be quite large. It might be very difficult to calculate the matrix Q. So I want to calculate it iteratively, not by direct inversion. And this is then our training algorithms. Let's assume that the xi are linearly independent, so that a solution exists. And then I want to find the solution iteratively by minimizing the energy function h of w, which is given as 1/2 sum over all patterns S mu minus st mu squared, with S mu is equal to S mu of w, and it's the sum over all I, wi x mu I. So this is the energy function I simply define. Because I'm physicists, I like quadratic functions, and there's a 1/2 here, and there's this h, so it's like the Hamiltonian, you know, it's all physics inspired. And you see that it has its minimum when all the s are identical with the st, the training examples. So if I succeed to find a w that actually does that, I'm at the minimum of my energy function and I've solved the problem. So in gradient descent, in gradient descent, what we do is we choose the delta W as minus eta times the derivative of the energy functions with respect to this Wi. The minus, because I want to go downhill, and this eta here is called the learning rate. It's typically a small number. That is a free parameter of the learning algorithm. So let's do the calculation with the energy functions. So in the energy functions, this S is a function of the W. So this gives minus eta some mu, S mu minus ST mu times ds mu times dwi. Okay, it's just the chain rule I use here. And then this derivative I can look up here because it's simply a linear function. It's easy to calculate, and the result is just xi mu. So here I have minus eta sum over mu S mu minus ST mu xi mu. So summarizing, in that case, for the whole vector, my training algorithm is minus eta mu sum over mu S mu minus ST mu times x mu. Okay, there are a few things to note here. First of all, in every training step, I present all my training patterns to the network because there is a sum here over all mu. And depending on that outcome here, I update my weights. And this is the comparison I've been writing here. So the difference between the outcomes is weighted in with the input patterns. Okay, and doing this training, repeating it possibly several times over all the input patterns will finally give the solution, will finally find the W. That can be proven. Yeah, and the second option is what is set up iteratively from the very beginning. So I call it iterative training algorithm, even though this is also iterative. Yeah, by the way, I wanted to say one more thing. You can also, in principle, just skip the sum here and define a learning algorithm that presents just one pattern per learning step, randomly chosen, and then it becomes a stochastic gradient descent algorithm, because then it will be random depending on which pattern I present to the network at a given time. This algorithm is a little bit different, and it's based on the geometrical picture we got here. But we will take that after the break, because the coffee is waiting for you and the cake. Please feel free to ask questions. Thank you.